Okay, this is section 2.3. We're going to be talking about functions in this section. Alright, what is a function? A function is a relation in which any element in the domain is associated with only one element of the range. That may or may not ring a bell, but hopefully talking about the vertical line test definitely rings a bell. So the graph of a function has to pass the vertical line test. Otherwise, it's not a function. Okay, so yeah, a function is a type of relation in which an element from the domain is associated with only one element of the range. Only one element of the range, not two, not three, just one. All right, let's talk a little bit about how to figure out domain of functions. Things to look out. So if you're given an equation, if you're given a function, the things to watch out for are definitely division by zero. Another thing to watch out for is negatives inside square roots or inside even roots, fourth roots, sixth roots. And another thing to watch out for is maybe a combination of dividing by zero and negatives inside even roots. So for example, here I have a function g of x. So what I would want to be looking out for here is what are the values that make my denominator 0? What are the values of x that make the denominator 0? Those are not part of my domain. Here's another example. Here's a function f of x. It's the square root of 3 minus x. I am interested in figuring out what values of x make the inside of this square root negative. Those values of x are not part of my domain. And then you have a function like this one, h of x, in which you have both a square root and some denominator. So those are the things that you're kind of watching out for whenever you're trying to determine domains. Also, it's going to be a good idea to keep interval notation in mind here, because in order to describe domain and range, we're definitely going to take advantage of interval notation. Okay, the story gets a little bit easier from a graph. In the case of a graph, well, actually, let's find the domain of these functions here. Let's find the domain of let's say this function g of x up here. Let me find the domain of g of x. So let me kind of go down here. So x minus 3. Now let me think about the denominator. It's probably a good idea to take advantage of factoring here. I'm going to express the denominator as x plus 5 times x minus 5. It's a difference of squares. Okay, well, then it becomes a lot more obvious. What are the values of x that make my denominator 0? I would say negative 5 and positive 5. Well, then my domain is everything except for those two values. Graphically speaking, let's begin by assuming that the domain is everything. But what we have discovered is that at negative 5 and at positive 5, we have little gaps. So there's like a gap right here at negative 5, and then there's also a little gap at 5. So my domain then is everything else that remains. So negative infinity to negative 5, parentheses. Parentheses are required right now because negative 5 makes my denominator 0. So I do not want that in my domain. Union negative 5 to 5, union 5 to infinity. I would say that that is the domain of g of x. What would be the domain of f of x? What's the domain of f of x? Well, what I'm trying to figure out are what are the values that make the inside of the square root negative. So one thing to think about it is, well, let me write down the function here. So I want to find the domain here. I want to find the domain. And if you think about it here, if my x is equal to, let's say, 3, then I'm going to have 3 minus 3 inside my square root. So 3 minus 3. And that's the square root of 0. And that's okay. That's just 0. What if my x happens to be bigger than 3? Let's say if my x happens to be like 4 or 5. Then I would have 3 minus 4. That would be negative. So it seems to me that what I should do, oh man, I don't know why this erases the whole line. What I should do is erase everything to the right of 3. Everything to the right, but 3 is included. So I think that's my domain. So I'm going to say right here that the domain is from negative infinity to 3. This time I am including a bracket with my 3. I would say that that's the domain of f of x. Now what's the domain of h of x? What's the domain of h of x? So let me go over here. Let me give myself a little bit of room. What would be the domain of h of x? This one's a little bit more complicated. The square root of 3 minus x over x squared minus 25. Because now I have to think about both of these considerations now. I do not want to divide by 0, and I do not want negatives inside my even root. Okay, so let's think about this. So for h of x, sorry, for g of x, for the function g of x, see the denominators were similar, and we said that we do not want negative 5 and we do not want positive 5 to be part of our domain, because those values make the denominator 0. So negative 5 and positive 5 should not be part of the domain. But now 5 should also not be part of the domain for the square root part, because 3 minus 5, that would be negative 2. So we don't want 5. 5 is bad. So from f of x, we said that the domain of f of x, which was just the square root part, that was from negative infinity to 3. So from negative infinity to 3, those are the things that make the inside of the square root positive. Those values make the square root, the inside of the square root positive. But in this interval, negative infinity to 3, it's the number negative 5 lives in there. So let's look at the little number line picture here. So I am thinking about from negative infinity to positive 3, somewhere in here is negative 5. And well, I should get rid of negative 5, because that would make my denominator 0. So I am going to go ahead and then think about this. So negative infinity to 3. So the values between negative infinity and 3 are okay, because then those are the ones that make the inside of my square root positive. But negative 5 makes my denominator 0, so I should get rid of it. And so then all the numbers that remain are my domain. So I'm going to say here that the domain for h of x is negative infinity to negative 5 with a parentheses, union, parentheses negative 5, 2, 3, bracket. That's the domain for the function h of x. Okay, so figuring out the domains for whenever you're given a function, an equation, requires a little bit of thinking. It requires a little bit of care. The story gets a little bit easier if what you are given is a graph. So if what you're given is a graph and you're asked to find the domain and the range, things are a little bit easier. So let's look at this little graph here. So it's a parabola. It's got its vertex at the point 1, 2, 3, 3, negative 4 down here. And I want to find the domain and I want to find the range for this parabola. Well, let's think about the domain. So if I am given a graph, so let me think about the domain of this graph right here. How far to the left does my graph go? How far to the right does my graph go? That's dealing with domain. So according to this little picture and these little arrows over here, this graph is supposed to keep on going forever towards the left. It slowly goes up and to the left and up and to the left. And this goes slowly up and to the right and up and to the right. So it goes forever to the left, forever to the right. So I'm going to say that the domain here is negative infinity to positive infinity. What about the range? What's the range of this function? Or what's the range of the graph of this function? Now we're thinking y values. So how far down did my graph go? How far up does it go in the y? So I would say that this graph goes as low in the y-axis or as low as -4. So it goes down all the way to -4. And how far up does it go? It goes all the way to positive infinity. It keeps on going up forever. So I am going to say that the range is bracket -4 to positive infinity. The bracket is because the point -4, or 3, -4 is part of my graph, so it's included. All right, so domain and range. Notice that I didn't ask you to tell me what's the range of this more algebraic functions, because determining the range definitely requires a little bit more information. Whereas if you're dealing with a graph, it's easy to determine both domain and range. All right, so let's think about the next things here. So a couple of definitions. When is a function increasing? So a function is increasing on an open interval I if for all a and b in that interval, if b is bigger than a, implies that f of b is bigger than f of a. That's quite a mouthful, but I sketched a little picture right here to sort of show you what's going on. So I have two values, a and b. This inequality right here says that b is bigger than a, so b is further to the right. And well, for my function to be increasing, if b is bigger than a, then f of b should be bigger than f of a. So the y value f of b should be bigger than the y value f of a. And that means that my graph is increasing. In a similar fashion, we can define decreasing. A function is decreasing on an open interval I if for all a and b in that interval, if b is bigger than a, implies that f of a is bigger than f of b. So similar little picture. I have that b is bigger than a. That's what this inequality is saying. A is smaller than b. B is bigger than a. So b is to the right, a is to the left. But now since things are decreasing, f of a is bigger than f of b. So things are going down. Now we have this other definition. Function is constant on an open interval I if for all a and b in that interval, f of a equals f of b. So here I have that a is over here, b is over here, and f of a is just equal to f of b. So that's what it means to be constant. So increasing, decreasing, constant. All right, let's put this to work. So I drew a little graph, a little function here. My little function starts over here on this leftmost point, and it ends on this rightmost point right there. And what I want you to find right now is find me the intervals on which the function is increasing, decreasing, and constant. So think about it, pause the video for a couple of minutes, see if you can answer this thing. You're gonna need interval notation to describe these intervals. All right, let me begin with increasing. Where is my function increasing? Well, intuitively, we know what increasing looks like. I mean, I would say that it's increasing right there, and it's increasing right there. Pay attention over here. This is, in order to describe these intervals, we need values of the domain only. So we're dealing with x values only, not y values. So what are the x values between here and here? I'm gonna say, so my x values are going to be from -9, right there, from -9 all the way to -5. From -9 to -5, I would say my function is increasing. Also, from about 7, because that's right there, to 10, my function is also increasing. But what's going on actually at -5 exactly? Is my function increasing or decreasing at -5? This is kind of a weird, strange point right here. It's a point at which you're neither increasing nor decreasing nor constant. It's kind of a point of change. And so then whenever I'm describing these intervals, I'm going to use parentheses for those points where it's kind of unknown the behavior. So we said that it's increasing from, I'm going to say, -10 to -5. I'm using parentheses for both because at these endpoints, I don't really know if my function is increasing or decreasing. I need to know further to the left here. Here it's kind of ambiguous. So from -10, sorry, not -10, it's supposed to be -9. From -9 to -5, my function is increasing. And we said that the function is also increasing from 7 all the way to 10. Those are the intervals in which my function is increasing. Where is my function constant? So I'm gonna say that this function is constant. Well, constant just means pretty much horizontal. I'm going to say that it's constant between 0, because remember, right now we're thinking x-axis, the domain, from 0 all the way to 7. Where is my function decreasing? Well, I'm going to say that my function is decreasing between -5 and 0. Between -5 and 0. Notice that I use parentheses here for pretty much everything, because at this boundary, like at these points where it changes from increasing to decreasing, it's kind of hard to determine if the function, it gets a little ambiguous there. That's why we use parentheses there. All right, next thing, let's talk about relative maxima and relative minima of a function. So this is a y value right here. F of c is a relative maximum if there is an open interval I containing c such that f of c is bigger than f of x for all x on the interval except for x. Yeah, that's quite a mouthful. I mean, but relative maximum. So if f of c is a relative minimum if there is an open interval I that contains c such that f of c is less than f of x for all x on the interval I, and x is not equal to z. What does any of this mean? So let's look at this picture here. I am going to say right now that that f of -5, I guess f of -5, what is f of -5? So let me go to, if my x is -5, what's my y? It's about 2. Let's just say that it's 2. So f of 2 is a relative maximum. Because for any x value that's around -5, f of -5 is bigger than f of whatever x value around here. And I am going to say, what about relative minimum here? I guess I'm going to say that f of 0, so what is f of 0? Let me go. If my x is equal to 0, my y is about -5. So f of 0, so -5 is a relative minimum value. Yeah? Don't worry too much about these intervals and whatnot. Right now, I mean, intuitively, this is a relative maximum value. Right now, we're talking about the y value. And this is a relative minimum value. Again, we're talking about the y value. Whereas earlier, with increasing and decreasing, we were talking about x values. So be careful with that. All right. So function notation, we've already been using it. So it's things like f of x, g of x, h of x, etc. Yeah. What it means is that think of the x as the input, the thing that goes into a little machine called f. All right, so let's get into some applications here. Let's write some functions. And let's use function notation. All right, so in this example, I had to, let's change the wording a little bit. Otherwise, it's kind of confusing. So a daycare center has, and I just erased what was here, and let's just change it to, so a daycare center has 30 feet of divider fence. So imagine that they just have like this little fencing for making little like cubicles and whatnot. So a daycare center has 30 feet of this little divider fence, with which they want to enclose a rectangular play space in the corner of a room. So they have two walls that are already given. Suppose that the play space is x feet long. Okay, we want to express the area of the play space as a function of x. All right, so take a second, pause the video, see if you can come up with an expression of the area. So a function of area in terms of length x. See if you can do that. So you want to end up with something that says a of x. All right, let's see. Let me sketch something here to kind of get us thinking about this. So we are in the corner of a room. So let me draw the corner of a room. All right, so that's the corner of a room. Those are walls. This is one wall and this is another wall. In these walls, we're supposed to use, now we're supposed to, use some of this divider fence and make a little rectangular pen. So this is a wall. So these are walls. This is the fencing. So I'm gonna put some fence there, and I'm going to put some fence there, yeah? So this is the fence. This is the fence that I'm using, and remember, I only have 30 feet of this fence. So these are the walls. This is fence. Okay. And they told me that it's a rectangular little area. Kids are gonna be playing inside here. We were told that the length of this rectangle is x feet long. So this length is x. Okay. Now I would like to get an expression over here for the, so this is my length. I want a width. And the width, I guess I'm gonna call it y right now because I have no idea what it is. But I hope that you agree that x plus y is equal to 30. I'm supposed to use up all this fence. That's the idea. So x plus y is supposed to be equal to 30. And well, from this little equation, because I mean, this amount of fence here plus this amount of fence, remember I only have 30 feet of that, so it's limited to 30 feet. And what I'm going to do here is, well, definitely solve for y. That says that that's 30 minus x. So I'm going to say, instead of writing y, I could have said 30 minus x. Hope that we agree so far. Now we want to come up with an expression for the area. Well, the area is going to be equal to x times y. It's just the length times the width. But I don't want to just say x times y. I just wanted, so right now for part A, we wanted to express the area as a function of just x, not x and y. So our only variable should just be x. Well, we know that y is also equal to 30 minus x. So then I'm going to say the following, that a of x is equal to x times 30 minus x. Because that's what y is equal to. I mean, that's saying the same thing, x times y. And that is my function of area in terms of length. And I mean, yeah, if you want to distribute the x, this would look like negative x squared plus 30x. And if you think about this, this is the equation of a parabola that opens downward. Yeah, this is a parabola that opens downward. What is the function? What is the domain of this function? What is the domain of this function? Since we're just dealing with a parabola, I'm going to conclude that the domain here is from negative infinity to positive infinity. My parabola goes as far to the left as whatever, and to the right also, it keeps on going forever. Alright, using the graph of a of x, we can use a calculator if we want to. We don't need a calculator. We're supposed to find the maximum area. Alright, so look at this expression up here. So a of x is equal to x times 30 minus x. This is already in factor form. And I also know that this parabola opens downward because there's this negative in front of my x squared. So I am dealing with a parabola that opens downward. What are the x-intercepts of this parabola? Well, the x-intercepts are where, I mean, we should have to set this equal to 0 to find the x-intercepts. And if we set this equal to 0, that's going to say that I have an x-intercept at 0 and another x-intercept at 30. So I don't really need a calculator to figure this out. Just a little bit of analysis tells me that I have these x-intercepts. And my parabola looks something like that. And so right now, I'm supposed to find the maximum area. Right now, this is x. Remember, x is the length. And right now, my y coordinate over here, this is a of x. This is the area. So my area depends on a length of my rectangle. And well, right now, what I'm trying to find is the maximum area. Well, the maximum area is going to correspond to this local maximum right here, also known as the vertex of my parabola. And I know that the vertex occurs halfway between the x-intercepts in this particular case. So what's halfway between 0 and 30? I guess it's 15. Well, that's not the area though. That's not the maximum area. 15 is the dimension of the length. 15 is the dimension of the length so that I achieve the maximum area. Well, then what's the maximum area? Well, I guess I would have to plug in 15 into my little expression, a of 15. I guess it's going to be 15 times 30 minus 15, which is just 15 squared, or 225. Okay, so I think that's it. I think we have found, and well, I guess the units here should be something like feet squared, since we're dealing with an area. This is, the units here are feet squared, the units over here are in feet. All right, so I hope that we agree with this this little problem here. Okay. Try the next one. Try the next one. Something similar. Something similar. Right now, what you're trying to do is you have 160 yards of fencing, with which you're supposed to enclose a rectangular flower garden. The garden is X yards long, you want to express the garden's area as a function of length. And what is the maximum area of this function? So take a second, try to do it on your own. I'll give you the answers here in a second. All right, it's a very similar idea as the previous one. It's a very similar idea as the previous problem. So we have 160 yards of fencing with which to enclose a rectangular flower garden. So let's see. Let's work. Well, actually, let's work it out. So let me write down. Let me draw a little sketch here. So I have. This is my length. My width is going to be what? So let's see. This is x. This is also x. And so I guess the relation that I have, if I call this y here, what I should have is that 2x plus 2y is equal to 160. So if I add up this length plus that length, this width plus this width, that's 160 yards. Let me get let me leave everything in terms of x. So let me solve for y here. So 2y is equal to 160 minus 2x. And so then y is going to be equal to 80 minus x. Okay. So 80 minus x. So then the area is going to be, well, x times y. But we want to leave the area just in terms of x. So it's going to be x times 80 minus x. Again, we're dealing with an upside down parabola that has x-intercepts at 0 and at 80. So the maximum area is going to happen at 40, when my length is 40. And the maximum area is going to be 1,600. So I'm going to say that the maximum area happens when x is equal to 40 and a of 40 is going to be 1,600. I guess right now we're dealing with yards, square yards. And this guy would be dealing with yards. All right, good. Let's see. The last thing in this section, piecewise defined functions. So let's graph some of these little functions and let's think about, yeah, let's graph one of them. You'll try the other one. Let's graph, I don't know, doesn't matter which one. I'll graph the top one. Let's begin, yeah, let's graph this one. And you'll come up with a graph of the other one. Okay, so I'm gonna use, I don't know, 2 colors. I'm gonna use green for the top part. So I'm gonna say y is equal to x minus 3. Let me first begin by graphing that. So this is slope-intercept form. I know that the y-intercept is at -3 and I have a slope of 1. So -3, that's -3. And I have a slope of 1. I go up 1 and over 1, up 1 and over 1, up 1 and over 1. Or I could have found the x-intercept, which is setting my y equal to 0. All right, so let me sort of join these points there. So there's my graph. This guy right here is y equals x minus 3. But you see this graph, I guess this line keeps on going down forever towards -infinity and all the way to +infinity. But I don't need the entire line. I only need the piece of the line that exists between that exists in this interval right here, bigger than 3. So if my x is bigger than 3, that's where that line happens. So let me go to 3. 1, 2, 3. That's when x is 3. And so for things that are bigger than 3, this line is occurring. So I really do not need this left part, so I'm gonna erase it. I just used it temporarily to sort of help me draw the line. And what I know here is that this should be an open circle because of the type of inequality that I'm dealing with. Oops. Because of this inequality. So that lets me know that this is an open circle right there. Okay. Let me sketch the other piece. Let me think about this piece right here. This guy right here, I'm going to sketch it in black. So I have y equals 2x minus 1. Let me think about first just graphing it. I'll erase the part that I do not need. So this has y-intercept at -1. That's right there. And it has slope +2. So from here I'm supposed to go up to and over 1, 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 up to and over 1. Okay, and then let me sketch this. Well, let me just kind of connect the dots here, something like that. I guess that's this. Yeah. Okay, and also I guess this kind of keeps on going up this way forever. But I only need, so for of this line, I only need the piece that's x's that are less than or equal to 3. So from right here, my x is 3 right here. So from right here, I only need the thing to the left. So let me erase the part that I do not need. So I do not need any of this. And this is a solid dot right there. And this guy right here in black, I guess it's my y equals 2x minus 1. And that is my graph. That's the graph of my piecewise function. That is the graph of my piecewise function. Definitely try graphing the next one on your own. Try graphing the next one on your own. Very similar. Right now your breakpoint should be when x is equal to 0. So somewhere here in the y-axis. Okay, well, this is it for 2.3. Thanks for watching, and I'll see you in the next video.